Hi, I'm Ben-Yaakov. This presentation is entitled A Primer to Multiphase Buck Converters. Let's see first of all what is a multiphase buck converter. Basically, we have a number of buck converters. I'm showing here a synchronous type converter, and synchronous means that we have a MOSFET here at the lower side instead of a classical diode. The reason is that we would like to lower the voltage drop when this branch is conducting. So we have a number of these synchronous buck converters connected, and they are actually connected in parallel at the output. That is, all of them are feeding the output. Here we are going to have the load. Now they are fed from a control circuit, of course, and I'm showing here the on time. That is the time for the upper transistor in each case. The lower transistor is the complementary pulse, of course, and these pulses are spread all over the period of the switching cycle. So these are turned on one at a time. There might be some overlap too, depending on the duty cycle. And the current is, of course, all funneled down to the output. So what would be the advantages of a configuration like this in general? And of course, we are going to discuss it in more detail later on. So the advantages are, first of all, we have load sharing. That is, the output is now shared by all these buck converters. So if we have a certain output current, we have N converters, then the current of each one of these buck converters will be I over N. Then it turns out we're going to have a lower input ripple. The input ripple stems from the fact that we are going to have here very heavy currents coming into at the input side of the power side of each of these buck converter, and the fact that they are working together one at a time is actually reducing the ripple. We are going to see it later on. Same time, we are going to have a lower output ripple at the output because we have these pulses coming one at a time. They are sort of canceling each other. We are going to be able to operate the system at a much higher switching frequency. Talk about it. We're going to have a wider bandwidth, and we're going to have a fast response to heavy load. That is, if the load is changing, we will be able to compensate for it and keep the output voltage stable. Now, the disadvantages are, of course, that this is a much larger system. We have many more transistors. The control becomes more complex, but this is what you pay for these features that you're going to have with a multiphase buck converter. Now, a multiphase buck converter is useful in cases where you're going to have a low output voltage and very high current. Now, this is now typical of today's processors that need very high current, and the voltages are going lower and lower as the size of the transistors in the ICs are becoming smaller and smaller. Then the voltage is going down and the current is going up and up. So a 1 volt, 200 amp is not an unusual requirement today. So let's see, why is it that we have to go to a multi-phase buck converter and a single buck converter isn't good enough? So let's suppose that we are going to build a 5 to 1 volt buck converter with 200 amp output, and let's assume it's running at, say, 200 kilohertz. Maybe this will be the upper limit for something like that. So here we have this buck converter, which is fed from a controller. We have the upper transistor and lower transistor, and obviously if we have an output of 1 volt and input of 5 volt, then the duty cycle will be 0.2. So this will be the 0.2 pulses of this transistor. Now this transistor now sees the inductor current, and the average inductor current is of course 200 amp. And therefore this transistor sees pulses here of current of, say, over 200 amp. This line is 200 amp, and for 200 kilohertz. The duty cycle of 0.2 implies the 1 microsecond turn on. So this transistor sees a 200 amp, 1 microsecond pulses coming through here. Now the lower transistor sees also this 200 amp, but it is on a longer time during the off time, which is 0.8 of the period, which means that in this case it's 4 microseconds. So the currents are heavy, and therefore the transistor has to be able to turn on and off in a very fast way. For these currents, this is going to be very heavy transistor, very large transistor with large capacitance at the input and at the output. So it'll be very difficult to turn it on and off, and of course the switching losses are going to be very heavy. The ripple that we are going to have depends on the size of the inductor, the switching frequency, and I'm assuming that I like to keep the ripple around, say, 30 to 50 amp peak to peak, the ripple of the current of the inductor, and that this is here the ripple of the current of the inductor. And let's assume that we require that the maximum ripple at the output, peak to peak, would be 50 millivolts. This is again very typical of a requirement for a processor or a FPGA. So we have a very big problem with the transistor. They need to carry very high current. They are going to have large power dissipation, whatever you do, because 200 amp, even if the resistance RDS on is very low, you're still going to have a high dissipation. And of course, you're going to have switching losses because it's very difficult to turn on and off the transistor very, very fast as you need to do it here. So what about the inductor? The inductor, of course, determines the ripple, and I've assumed that I like to keep the ripple, say, around 30 amp. The average current of the inductor we know is 200 amp. Well, it says here 150. Actually, it should be 200, the example that I'm showing. And during T on, the current is rising. During the T off, the current is decreasing. And this is the situation during the T off. The lower transistor is on, and we have 1 volt here. And from this slope and the state space equation of the inductor, we can calculate the inductor inductance that we need. And it turns out that with 30 amp peak to peak, and this time is 4 microseconds, we need 130 nanohenry. Now it looks like it's a small inductance or a small inductor, but it is not, because the size of an inductor is given by this equation. Now this equation is the AP, this is the area product, and the areas are the cross-section area of the core. This is the core of the inductor, this is the cross-section area, and A sub W is the window area. So the product of this area times this area is given by this equation. Now this equation says that this area product is equal to the inductance times the peak current times the RMS current divided by the B maximum you allow. J is the wire current density, and K is the filling factor, that is how well you can put the windings together. So the size of the inductor is going to be determined by a large extent by the current, and the product here sort of resembles I squared, which means that the size is proportional to the energy actually stored in this inductor. And with 200 amp, and the I peak will be much larger, it will be 200 plus 15 volt. It's not going to be a small inductor, it's going to be a large size inductor, despite the fact that it looks as if it is a small inductance here. So we're going to have a problem with this inductor, and then Similarly, we have a problem with the output capacitor. Now, the output capacitor has to carry the ripple current because we'd like here to be almost a DC with small ripple on it. So most of the ripple current of the inductor has to pass through the capacitor. Now, we have assumed a 30 amp peak-to-peak ripple current, and we can calculate the ripple voltage by just integrating here, looking at the total charge of the ripple, and this turns out to be approximately, I'm just assuming that this is halfway and this is a triangle, so that we have this delta I peak-to-peak 30 over 2, which is 15, and then the period here, half the period, I'm sort of dividing this into two parts, and area of a triangle is then height times base times divided by 2. So this comes to be like 2 to the 10 to the minus 5 coulomb. And since I want a ripple of peak to peak of 50 millivolts, then it turns out that I need a 40 millifarad capacitor. And so that's 40,000 microfarad capacitor. So this capacitor is going to be very big to accommodate this high ripple current. Now, this doesn't end the story here because we have another problem when you have a change in the output current. This shows the output current, and here I have a ramping up of the load, say the FPGA started to run, and then usually the specifications are in terms of amp per microsecond, and it could be something like a few hundred amp per microsecond. This is how fast the load is changing. This is the delta I change that we have. And during this time, we are putting now a much higher current. The problem is that the inductor current was low. This was the inductor current before this ramping up started. And it takes time for this current to build up because we have the IDT is V over L, and the maximum voltage we can impose on this inductor is V in minus V out. So this is the maximum the IDT, and so it takes quite a bit of time for the inductor current to ramp up from this low value to this value. Now, during all this time, the current is still flowing to the load, and it's coming from the capacitor. Now, since there is no supply of current from the inductor, and the current is pulled from the capacitor voltage will drop. And this drop has to be maintained within a given specification, or we say something like 40, 50 millivolts. So this again imposes a requirement of this capacitor to be very large. So we see that one buck converter makes it very difficult to supply a low voltage and high current as is required in many applications today. So we come back to the multi-phase buck converter. Now, as far as the transistors go, the situation here is much, much easier. The current carried out by each one of these buck converters is, of course, much lower depending on the number of phases that we have here. So there's a load sharing. Therefore, we can have a faster switching frequency, a few hundred kilohertz without penalty of heavy switching losses. And as far as the transistor situation is, of course, much, much easier. Of course, we have many more transistors here than the single buck converter. What about now the output ripple? Let's consider the very simple case, which is very illustrative here, of two buck converters. And let's even take the very unique case of a duty cycle of 0.5. And therefore, we're going to have the duty cycle of each one of these buck converters uh, displaced in half of a period, and therefore the ripples are going to be shifted by, say, 180 degrees, and therefore they're going to sort of to be in opposite one to another, and therefore the sum of these is going to be zero. So in this very particular case of two buck converters operating at duty cycle of 0.5, we're going to have zero ripple at the output, zero current ripple at the output, and therefore this capacitor could be much, much smaller. Now, if the duty cycle is not 50% or 0.5, then of course the ripple would be higher, depending on the duty cycle. This is the duty cycle in percent. This is the singular point of zero, but of course in other duty cycle we have to have still a lowering of the total ripple. Now in a multi-phase system, and these are the cases for 2, 3, and 4 phases, could be even more, we see that, let's have a look at the 4 phases. For duty cycles, say between 0.2 or even 0.1 to 0.9 or 0.8, the maximum ripple is going to be much, much lower. So this, of course, simplifies the requirement of the output capacitor that doesn't have to carry the heavy current of the output. Now, what about the input? Well, each one of these transistors, the upper transistor, is turned on its own time, and therefore there is also a cancellation of the ripple current coming off the input capacitor. And this is the picture here for cases up to 4 phases. Let's have a look at the 4 phases. We see that the ripple current is indeed very, very low as compared to the single phase. Now, in this case, there are some singular points, but even if you are off these points, the ripple at the input is much lower. As far as the slew rate goes, we effectively see these inductors, in fact, in parallel, because say there is a need for a higher current, then all the duty cycles are going to be turned on or to become larger. So in general, we can say that the equivalent inductance here is the single inductor divided by n. This is the number of phases. The same token, since the inductance is lower and the capacitor is lower, we're going to have a much higher resonant frequency or breakpoint, you might say, of this LC network, and therefore the bandwidth of the control could be much higher than the single inductor or single buck converter, in which the inductor and capacitor are large. There is a problem, however, that one has to watch and solve, and that is the possibility of imbalance between the current. And here again, I'm showing 2 buck converters, sort of a multi-phase operation or 2-phase operation. Now, if the currents are not balanced, that is, the amplitude of the current here is not equal to this one, then of course we are not going to have a good cancellation, not to mention the fact that one of the buck converter will have a higher power losses than the other one. So in general, there is always a need to sense the current and correct for it. The correction is of course done by adjusting a little bit the duty cycle until the current are equal. But the key point is that you need information about the current, so you have to sense the current. Now these are heavy currents in the multi-phase converter, and putting a resistor say in series with the inductor to measure the current leads to high power losses. So there is a need for a sort of a lossless current sensing in this situation. And there are actually a number of methods that I'm going to cover very quickly. One of them is to use this auxiliary RC circuit. So what we have here, this represents an inductor. This is the inductance, and this is the DC, or actually AC, it should be resistance, the parasitic resistance of the wires of this inductor. The idea of this method is that we are actually relying on the fact that there is a voltage drop on this inner parasitic resistance, and we are going to actually measure this voltage drop as a measure of the current flowing through the inductor. There is a slight problem here that this resistance is somewhat dependent on temperature, so this is something to take into account. But in general, the idea is to look at the voltage drop of this parasitic resistance. Now, obviously, you don't have any access to this resistance, so you have to measure it somehow from outside. This is the outside of the inductor. And this is done by this RC circuit, and can be easily shown. I'm going to show you very quickly that the voltage that you'll see on this capacitor, this voltage V sense here, is actually proportional to this parasitic resistance, and therefore proportional to the current that is flowing through this inductor. So let's first of all consider the DC situation. The DC voltage on this parasitic resistance is just the DC current times the resistance. Now, the voltage drop of the inductor in the DC situation is 0, so therefore you have here the same DC as you have here, and therefore, since there is no DC current flowing through the capacitor, you do see here the DC voltage of this resistor. So you see here the VDC here is the IL times RL. This is what you see here. Now, what about the AC component, the ripple, the high frequency component? Okay, suppose we are feeding here. Let's talk about one of these high frequency components, whatever frequency it is, say the first harmonic even or any other harmonics. When you feed here an AC signal, since the impedance of this inductor is much lower than this auxiliary circuit, that's going to be a fairly large resistor, you might say that all the current is actually passing through here, and therefore the voltage drop on this resistor, this parasitic resistor, is proportional to the actual inductor current on this total current. Okay, so this voltage drop on here, and in fact on the inductor itself, is equal to IL, this is the AC component, times the impedance, this is the Laplace presentation of this branch. Okay, this is the voltage drop here. And now from here we have a voltage divider, which is this voltage divider. And working this thing out, we find that the output voltage on this capacitor, the AC component, is IL, AC component, times RL, exactly as we have here, times this function. Now here we have two time constants. This is the time constant of the inductor itself, and this is the time constant of this auxiliary circuit. So if we make this time constant to be equal to this time constant, this becomes 1, and therefore we are going to have this voltage here to be equal to the current times RL. So again, we see that the voltage across this capacitor is actually representing the current through this inductor, both for the DC and the AC component. Once we have information about this current of the inductor, we can of course compare this to the other inductors and then readjust the duty cycle when needed in order to adjust the current. Now, there are two other methods which are used, which are again sort of lossless to measure the current that some manufacturers are using. One is to rely on the fact that when the lower transistor is conducting, the voltage drop on it is of course proportional to the current through the inductor. Now, the voltage here will be the current times RDS on. Now, if when this transistor is on, we will sample this voltage. We'll have here a measure of the current through the inductor. Of course, we have to assume that we know RD is on. Another method that we can use is to use a so-called a mirror transistor. Preferably, these two transistors should be the same die, same transistor. This is the main transistor, this is the upper transistor, and this is sort of a mirror of this one, the size of which is much smaller than this transistor. Technology should be the same, so that the relationship between VGS, the voltage here, and the current will be similar in these two transistors, except for the fact that the smaller transistor will have a proportionally lower current. So once the voltage of the control is high, these two transistors are conducting, and we have the current through this main transistor coming out. We'll have a current here, which is proportional to this one divided by n. This is the ratio between the sizes of this transistor, and we can get the voltage drop of this resistor, which is proportional to this current, and we have a sense of these of the value of the current passing here, which is the inductor current. So these are the two sort of a semiconductor-based method for measuring. Then the multiphase converter. We have a number of buck converters, and of course we can see that at high current it's very effective. But what happens when the current is lower? That is, in a real system, you don't run it always at the maximum current. You have to accommodate situation in which the current is low. Now, if this is the inductor current and the current is becoming smaller and smaller, you move into the situation which is shown here, in which the current actually will be bipolar. The reason is that when this lower transistor is turning on during the off time, current can flow both ways. It will go this way, and then if it comes to zero, the current will go back. So we're going to have a current circulating here, which is just wasting energy. There's a losses involved in conduction losses, but the average current is very, very low. So this is a situation that you really don't want to happen. So one way to overcome it would be to sense this situation, and when the current is hitting the zero, to actually turn off the lower transistor and having a preferably Schottky diode in parallel, so the current will pass, the positive current will pass here, and when it comes to zero, there will be no current at all. This is very similar to a regular buck converter with a diode here. So this is another feature that can be added. Something else that, of course, can be invoked is the so-called phase shading. That is, as the current is becoming lower and lower, you don't need all these phases, so you can sort of turn off some of these buck converters and eventually be left with only one. So this is something that is related to the control system that is feeding these buck converters. As an example, this is just from a Texas Instrument data sheet or application notes. They are showing here what is happening with a 5-phase converter. This is just an example. There are many other companies, of course, making similar control units, and they have similar evaluation boards. And what they are showing here is a situation in which the current is starting from zero, say, to the maximum of, say, 200 amp. And at the beginning, there is a one-phase DCM. I have mentioned that this is, of course, this situation is called the DCM. And then the system goes into one-phase CCM, one phase here, and then as the current increases, two phases are brought in, and then four phases, and then eventually the five phases are operating in this region of current. Okay, so this is something that the controller can handle. I'm now going to show some details of a evaluation board, a reference design by Texas Instruments. This is just an example. There are other companies who are making these evaluation boards and also the ICs, the controllers, etc. And there's no endorsement here or recommendation. This is just an example that I've taken to show some of the details that we have discussed earlier and see how they are implemented. So what we see here is a board of a 150 amp of about 1 volt output. This is for an FPGA. And we can see here 4 inductors. So this is a 4-phase multi-phase buck converter. These are the drivers. These are the transistor assemblies. We will see them in a second. And this is actually the controller. What we see here, of course, are all these capacitors which are spread out and some auxiliary controllers that we'll talk about. And this is this board with inputs and output. This is a 12 volt input, we'll see it in a second, and a 1 volt, about 1 volt output. So this is the basic configuration of the system. It's a 4-phase controller. This is a TI element. Then we have, they call it smart power stage. This is a transistor assembly plus some other units inside, like current sensing, which are inside here. So this is a composite assembly, not just 2 transistors, and all these are then connected in parallel at the output, and there is a output side. Now, on board they have a load generator. That is a way to load the converter, so to see the response to a load change, and also they have a connector for an outside so-called Intel load slammer. This is again a heavy load just to see how the system responds to a current change in the output. Now the design specs are input of 12 volt, output of 0.9, the switching frequency is 600 kilohertz, and the target ripple is 2%. We are talking about maximum current of 150 amp, and it has to accommodate a 75 volt delta I increase or decrease in current with a 500 amp per microsecond slew rate. We talked about it earlier. So this is the controller. I'm not going into the detail of the controller, just to mention the 2 facts that it has an output. These are the PWM outputs to the drivers and transistors. And here we have inputs. These are the inputs from the current sets. Okay, so we have information about the current of the inductors, which are of course affecting the current sharing here, and the controller can then, therefore, with this information, make sure that the current of these 4 phases will be the same. Here we see the actual drivers. What we have inside is, again, the transistors plus the auxiliary circuits. We have, of course, drivers for the transistor, the gate driver for the transistor. They are here because from the controller we just have a signal which are not sufficient to drive the transistor. We have also to split them into the lower and upper part. And then we have a bank of capacitor, which is the total output capacitance. It's made of a ceramic capacitor connected in parallel. The big ones are 220 microfarad, and counting them down, it's about 10 units of 220, so it's about 2 millifarad, 2000 microfarad total capacitance that we have here. Let's have a closer look at one of the drivers. This is the inductor. It's a 150 nanohenry per phase. This is just a snubber. This is a capacitor which is used to charge the sort of power supply of the upper driver for the upper transistor. It needs a power supply, and this is sort of keeping the voltage for the driver. And then, of course, we have the ripple at the input capturing by these capacitors, and this is the input to the this is coming from the controller, the PWM signal, and this is the information about the current sensing. I don't know exactly how they do it. They don't give it in the datasheet. It's probably one of the semiconductor type measurement I mentioned. Now, the capacitors are spread out. As I've said, these are ceramic capacitors connected in parallel. The reasons that in parallel to 220 microfarad, you are going to put 0.1 microfarad, which is kind of strange. You already have 220. Why put in parallel 0.1? Well, the reason is that the capacitor has inductance and resistance. This is just showing in a pictorial way what's happening on this board, in which you have many capacitors and they're interconnected. The interconnection also has inductances and resistances, and if a larger capacitor will have a larger inductance. So therefore, you like to put a smaller capacitor with a smaller inductance in order to accommodate the higher frequency in which the high capacitance capacitor has a large inductance. So the situation is rather complex, and the layout is really not trivial here. And this is the reason that you had put both high value capacitor in parallel to small value capacitor. Now, aside from the unit itself, this is an evaluation board. As I've said, they have a connector for an outside load to be able to test for the load stability or load change stability of the unit. And here are some measurements that were taken. This is for 100 amp output, 0.9 volt. Here we see the pulses of the upper transistor of one phase. This is a frequency of 600 kilohertz, and as you can see, the ripple here is really small. This is the resolution here is 10 millivolts for this one, and this is from here to here, it's 10 millivolts. So this is about a few millivolts of ripple. This is in the steady state. Now, the actual test of the unit is not a steady state, but really with a load change. And here we see a load change of specified to be 500 amp per microsecond, and the delta here is 75 amp. And what we see here is as the current is increasing, there is a drop. And as I've explained, the reason is that the inductor cannot supply this current. So this drop represents the effect that we are taking charge out of the output capacitor, and it is dropping down. Now, the same goes here when we are shedding the load, and when we are turning it off. Then, of course, the inductor still has current, which is flowing out from the inductor to the output, while the load doesn't need this current. So this current is now accumulating, or the charge is accumulating on the output capacitor, and therefore there is an increase in the voltage of this output capacitor. Now, the resolution here of this trace is 50 millivolt, and this is 15. So this is about 30 millivolt peak. You have a change here for this 75 amp delta I, which is ramping very fast. As I've said, there are many other companies who have similar products, and this is just an example of a on-semi product. This is the controller. Now, the situation here is a little bit different. This is a driver, this is a two-switch assembly driver, but here, as you can see, the current measurement is done by this RC circuit that I have mentioned earlier, and these two lines are now get fed to the controller, these two lines, and of course this has to be a differential amplifier because this voltage here is the output, so the voltage that we are interested in is the voltage across this capacitor, and these are of course used with the other ones to control the PW. This brings me to the end of this presentation. I hope you enjoyed the presentation, and I hope it'll be useful to you in the future. Thank you.